Yesterday we talked about parametric coordinate systems, and today we explore even another type of coordinate system. So to start, we have the classic rectangular coordinate systems that identify a spot on the grid by an x and a y, horizontal and a vertical. We also have parametric now that is in some ways more like an ordered triple. You have an input of t, and you have an output of x relative to that t and y relative to that t. It still plots points on the grid, and it's still somewhat rectangular, but it's more of a function that goes from real numbers to an ordered pair. It inputs a real number t, and it outputs a real number in two dimensions, x sub t, y sub t. Whereas in this rectangular, you input an x and output a y. So it's more like a function that goes from a real number to another real number, x to y. Now, the third type is a polar coordinate system, and this is what we're going to be spending the next couple of days to even weeks doing, where it's kind of variable as to whether our input is one or the other. I tend to use the input is theta and the output is radius, because you're going to see functions defined that way. Your book actually flips this and does radius comma theta, but it should be easy to tell based on which where the pi's are, which one's the angle. Also, any good book's going to define what coordinate system it's using, so I'm going to define this in terms of theta and radius. So we have seen angles on the grid before, and if I draw a grid and kind of put an angle down, my angle theta is not just an angle, it's a directed angle, meaning it has a positive and negative side. It's a directed in that I know that clockwise is negative and counterclockwise is positive. So it tells me where I'm moving relative to that. Now, every good coordinate system has a sort of origin, so if I look at where the polar origin is, my angle right here of 0 and my radius of 0, this acts as a polar origin. Polar origin occurs where r equals 0 and theta equals 0. Now, my directed angle, I should say directed, my directed angle is also determined by a radius. So if I look, I've got a positive radius wherever that is, and we also now can have a negative radius, which would occur basically 180 degrees, or pi radians on the other side. So wherever my angle is, you can have both a positive and negative radius. This day is going to be relatively easy. You just have to kind of learn a new system here. So some examples of this, if I were to ask you to plot on the same grid, and meaning just we're going to plot these points. This is what we do when we first teach you rectangular or Cartesian coordinates. We just ask you to plot points. So let's plot the point pi over 3 comma 2. Let's plot the point negative pi over 4 comma 3. Then let's plot the point 5 pi over 6 comma negative 4. And then let's plot the point negative 2 pi over 3 comma negative 2. So this looks like what a grid could look like in polar coordinates. And if I plot pi over 3 comma 2, what I'm saying is the angle pi over 3 and a radius of 2. That would occur here. This would be point A. Then if I plot negative pi over 4, which is to go backwards, and then a radius of positive 3, that's along that line. So along this negative pi over 4, I'm going to plot a radius of 1, 2, 3. That would occur here, and that would be point B. Zoom in a little bit more. My next point, D, was 5 pi over 6 comma negative 4. So if I go 5 pi over 6 to here, but I plot a negative 4, I need to appear 180 degrees on the opposite side. That would be at 11 pi over 6. 1, 2, 3, 4, and that would occur right here, point C. Finally, if I plot negative 2 pi over 3, Now, negative 2 pi over 3 is coterminal with 4 pi over 3. So that's going this direction, negative 2 pi over 3, or 4 pi over 3. So that's this angle here. And then negative 2 appears on the other side. Well, that's the same as this point A. So A and D are actually the same ordered pair. These are actually the same place. Okay. The next major thing is this conversion between coordinates. Conversion of coordinates. So to go back and forth between the two, we have a nice system to convert from polar to rectangular. Well, given a point theta comma r in a polar form, if I want to take that and convert them to x, y's, we already know how to do that. I know that if I have a right triangle where I have a radius and an angle, to get x and y, we have relationships based on the trig functions between those in a right triangle. I know that the sine of theta is equal to y over r, and I know that the cosine of theta is equal to x over r. So solving for x and y, I know that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. This is essentially the horizontal and vertical components of motion for those of you that are in physics, and have kind of tackled that already. Now to go backwards, to convert from rectangular to polar, well, if I'm given a point xy in rectangular, then theta would be equal to, well, I know that the tangent of theta is equal to y over x, so theta is equal to the arctangent of y over x, but we have to pay attention to the quadrant. And the quadrant should be evident from which quadrant x and y are in. Then all you have to decide is radius. Well, we also know a relationship between x, y, and radius. I know that x squared plus y squared is equal to r squared. So r would be equal to the square root of x squared plus y squared. So given these two, and paying attention to the quadrant, we should be able to very well pinpoint a polar conversion from rectangular. So let's do some examples of this. So I think we're at number 2. If I have, if I want to convert 5 pi over 6 comma 4 to rectangular, well, I know that x would be equal to 4 times the cosine of 5 pi over 6, and y would be equal to 4 times the sine of 5 pi over 6. So really this just comes down to making sure you know your trig. 5 pi over 6 is an angle in quadrant 2. It's a 30-degree angle, 30, 60, 90 triangle. If I draw that with a height of 1 and a radius of 2 and an x value of negative root 3, and just start putting the different values in, I know that 4 times the cosine is negative root 3 over 2, which is negative 2 root 3, and then 4 times the sine would be 4 times 1/2, which is 2. So then my ordered pair would be negative 2 root 3 comma 2. Next step, to convert to polar. So if I wanted to take this and convert, let's take the ordered pair, let's take a basic 1, negative 1. If I want to convert that to polar, or 1, negative 1, you can graph and take a look at it. It's right here in quadrant 4. If I want to convert that to polar, I know that r is equal to the square root of x squared plus y squared, so 1 squared plus a negative 1 squared, which is root 2. And my theta is equal to the arctangent of negative 1 over 1, which is the arctangent of negative 1. Now, arctangent of negative 1 would output negative pi over 4, which is fine. unless it asks us for an angle between 0 and 2 pi. And if it does, we want to make this become a coterminal angle at 7 pi over 4. And I would express my ordered pair as angle 7 pi over 4 and radius root 2. Obviously there's an infinite number of ways to express them in polar form, which is pretty unique that there's an infinite number of ways to express an ordered pair in polar form, but just one way to express it in rectangular. Okay. Next, we're just going to practice a graph. So we're going to graph r is equal to 2 sine of theta. I want you to graph that, which means you pretty much have to know the shape. Well, this is a matter of doing conversions. I'm going to try to graph it by converting to rectangular and see if it makes a familiar shape. I can do that because I know that the sine of theta is defined as y over r, and if you multiply both sides by r, you get r squared is equal to 2y. Well, r squared is just x squared plus y squared equals 2y. And that's an ellipse. It's actually a circle. You get x squared plus y squared minus 2y. And if you complete the square, add 1 equals 1. You get x squared plus y minus 1 squared is equal to 1. And if I graph that on a grid, that's just going to look like a circle with a center at 0, 1 and a radius of 1.